Welcome to another episode of the Semi-Related Podcast. My name is Jacob Eischen, and I'll be your host today. And I'm joined by Dr. Uster. Doctor, how are you today?
I'm good, Jacob. Thank you for having me.
Of course. Thank you for being here. And I want to bring on Dr. Uster here because of some great work he's done in research. He presented here at Optum's headquarters a few weeks ago and shared a little bit about his research, but thought this would be a great opportunity for him to dive a little bit deeper and share some of his knowledge with our audience. So if you want to give a quick background about who you are and kind of what you're working on and maybe even how you've got to where you're working at today, that'd be a great starting point.
Sure. My background is actually, if you go too far back, I'm a mechanical engineer by training. And I actually worked as a mechanical engineer too, in designing and then implementing the systems of a hygiene plant in Turkey. I'm originally from Turkey. And about the second half of that, I said maybe it would be a good idea to get a master's in business. That seemed to be a necessary thing at the time. At least I thought that way. And then I started that, and then I moved into academia being a teaching assistant. And then that was a time that I was looking to decide really what to do next. And academia and industry all of a sudden presented itself as the two options, and I chose academia, knowing that I can always do some applied work even when I'm in academia. So this is how I moved into academia, uh, and then one of really the determinant points along that, I'd like to mention that actually that I took a course on systems analysis. And in that course, the professor asked us to read that book called Systems Approach by West C. Churchman. And he's one of the founders of operations research. And that book was so inspiring to me at the time. And it just opened up a whole new world. I mean, it sounds like cliche, but I was just so excited after reading that book, and then that really made me just choose academia for certain as my career path. And then from then on, I started looking into PhD and got my PhD at McMaster in management science and systems in the business school, and then moved to Alabama for 1 year, University of Alabama Industrial Engineering Department, and then moved to Texas A&M Business School for 2 years. I was there. Those were visiting positions, and then I started at Texas A&M Industrial Engineering as a tenure track faculty at 2002. And 2014, I moved to Southern Methodist University, SMU in Dallas, as a professor, now in the Operations Research and Engineering Management Department. So we just renamed the department couple of years ago. So it's Operations Research and Engineering Management Department there. So I've been here for the last almost 11 years now.
Well, you said a few things in there that stuck out to me. The applied was one thing that stuck out to me, and then another one was passionate. And talking to you on before we started recording here, we kind of were going over some of the research and work you've done, and I think you're still very passionate, and you're always looking for new ways to apply some of your research and what you've done. So if you want to give like a quick overview or kind of run through about some of those things that you've been working on, and then we can dive a little bit deeper and maybe talk a little bit about what we were discussing before we started recording.
Sure. So in general, I work on the applications of logistics networks and optimization, modeling and optimization, and some analysis, of course, to understand those systems better, to make decisions, first and foremost at the strategic level, and then going down into tactical and operational decisions after that. So in the logistics context, of course, there's a lot of different applications that you can find, but the specifically that the ones that I work on include one, the transportation networks, freight transportation, relay networks specifically in that context, and another one that we work on is on the emergency preparedness networks, and another one on the biomass supply networks. So there's several others too, but those three that I can mention, and in all of these, like I said, we try to look at it from the strategic perspective first, and from a systems view, understanding the objective and the components of the system, and then how they interact, and take that into consideration when we are modeling for these systems, and then when we are doing the analysis to really understand those dynamics between those different components, and the trade-offs involved. So in the relay network setting, that started early on, actually, in my career. I was just looking into different studies, and actually I was designing a course. The first time I came across some of the studies in freight transportation for truckloads, right? It was during that time. My colleague Don Taylor at Virginia Tech, he has a great set of studies on simulating different operational paradigms for truckload transportation. So we looked at those, and then we said, okay, like, where do these networks come from? Can we design these networks? How would we design these networks? And then I started working with a master's student of mine on that, Nimish. And Nimish actually wrote his master's thesis on that. And as we were thinking about setting up those networks, we said, okay, we cannot just look at it as a transportation network that's operated by a company. But here the issue is driver turnover. Now driver shortage. Driver shortage was not talked much back then, but turnover was a big issue, especially in the truckload industry, almost like 100% persistently. In a way, meaning that every year you have a new roster of drivers, right? And there's a lot of cost associated with that, without not producing anything. It's just a waste in a way, right? So, as we were thinking about setting up the networks for that, it occurred to us that, okay, it's not just the company's point of view, but we also have to take the driver's point of view. But that's not enough. Also, the customer's point of view, right? So they have different objectives coming into the picture. So how do we design systems and operate in a way that all these stakeholders, we call them stakeholders in that system, are going to buy into it? Because it's a new thing. I mean, it was not easy. I was chasing some professionals in the conferences. Like, I was telling them about this and trying to get some data and all this, but it was always like, oh, but it's not going to work. It is too difficult. This, we don't set up like this. Our operational paradigms are different, kind of thing. So I knew that it was an upward battle, but it was that's what we do in research, right? So we just keep working at it to see where the value is, and how can we make it work in a way, right? And in that avenue, it was clear to me that we have to take all stakeholders' point of view into account. You cannot just do it for one. You need buy-in from everybody, right? In a way. So when you look at it, then for the drivers, it was very important that they don't go too far away from their homes. They have predictable schedules, right? And they still make money, right? And that's directly related to how many miles they drive. So if they're sitting in some truck stop and at some gas station, parking is another issue, of course, right? And they have to find the parking and all that. They're not making money, right? So how can we just let them be driving most of the time, but still make it back home on a regular basis, right? But if you look at it from the company's perspective, cost is of course important. That's one of the things, because they own those systems at the end of the day, right? By and large. So circularity is an issue. You're not going to find a dispatcher that will say that, okay, this is the shortest distance from A to B, but I'm going to send it like this, and I'm going to add 300 miles to it, right? This is hard to justify, right?
Yeah.
I mean, we don't add that much, so to speak. So it's an issue that needs to be attended, right? When you're designing those systems. And then empty dispatch, of course, they don't want any drivers driving without any load attached in the trailer, right? So that's why they keep the drivers out there too long, because they're waiting for the next load for the driver, right? To avoid the empties. But the company, they also want the drivers to stay. So that's the challenge there. And then equipment, of course, has to be in tip-top shape, right? It has to be utilized. It has to be maintained. It has to be tracked. Visibility is important. If something goes wrong, it has to be repaired quickly so that it's back into production, because that's the machinery that they use for their business, right? And then there's the hours of service regulations, right? So you have to abide by those. That's the driver can only drive so many hours and they have to rest, right? So that's important. Carbon emissions became a big thing. We don't want idling. The parking and waiting in, I don't know, 10 degrees Fahrenheit, even, out there, you're gonna idle. That's how it goes. And a lot of trucks, in the parking lots, idling, that's not a good idea. And deliveries, of course, on-time delivery is important, right? You don't want the load sitting somewhere that's hard to track and all that. And then the customers, of course, they want delivery times, they want lower shipment costs and all this. So putting it all together, we said, okay, there's no magic here. So you have to satisfy all these things, make everybody happy. So this is sort of what kind of moved us. First it popped up, and then we were able to justify it to this relay idea that the loads are traveling from their starting point. We're talking about truckload here, obviously, right? From O to D, go to a relay, and then from relay to relay hop, and then delivered to the last location, right? The destination location. So there, how do we set up this network, and how do we route the truckloads between those cities, right? So if it is going from Dallas to Chicago, what are the relay points in between where the drivers are going to be just taking the loads back and forth on these links, connecting the relay points. And so they're staying always in their domicile. So, and that was not very difficult to justify, at least on paper, I should say, because that's what makes it difficult to sell, right? So you can justify it, but then in operation, of course, things can differ. So this is why we try to bring in some operational realities into the equation. And it was easier to justify in the sense that when you have a system like this, you have strong backbones with a lot of traffic. So you have drivers and a lot of opportunity to drive back and forth, right? And they have more predictable schedules, right? Especially at this time and age, you can predict the loads, right? And I'll actually come to the operational side of it. And then from the company's perspective, circularity is important, but that when we're designing this, so we have to take that into account. How do we control the circularity, at least write a constraint on it, right? And then, of course, the equipment utilization, maintenance, repair, those things, when you have these relay points, they provide the perfect opportunity to keep your fleet in a tip-top shape, right? Get it clean, get it maintained, oil change, check the tires and all that stuff. Get all these things done there, not stranded, somewhere, right? And so it provides that opportunity. And the drivers, hours of service regulations, so that's another way to really limit the distances between those locations, maybe another way, because the driver once gets to a relay point, then they can rest there. But the load can continue. So that actually improves delivery times, right? Because the load is not just resting with the driver. So it keeps moving in that backbone. And the carbon emissions, of course, in those facilities, you can have the trucks maybe plugged in, or or some other thing, and not just the parked somewhere, and more importantly, drivers can actually, they don't have to be in their trucks, right, before they come back, and you can have facilities for them, and so on and so forth. So this is all benefiting actually the customers too, because loads are delivered quicker, and all this wasted cost is out. So that affects the shipment costs as well, right? The deliveries are on time. Total delivery times are quicker. So it was like a lot of win-win cases, right? Situations there. But from incorporating the operational realities perspective, there are a few things that you have to really take into account. One is circuity that you have to control. The other one is that when you're setting up a network like this, you have to be watchful of the distances between those things, because that's the starting point. So you have to incorporate that, right? And of course, the load imbalance is an important point there, because you want to minimize the empties. So we started with the load imbalance at the nodes, but then we moved to link imbalance, that is between the relay nodes. We try to minimize the difference between the back and forth number of loads, so that the matching is easier, right? So we take those into account. So, and then there's some uncertainties. We brought in the uncertainties into that. And at one point, this research was supported by National Science Foundation. And we really appreciate that support. And another graduate student was funded by that. So we still work on this research. And we have shown that actually this real data is very difficult to come by because of a lot of things. But what we try to do is that when we are generating our test data, we use whatever that we find, and then we generate some other data randomly on top of it, and then we do our analysis on this. From the transportation costs perspective, which is the most comparable part that actually makes the companies really adopt that, is that we can actually show that you can have benefits up to 10-11%. Which is very encouraging to us. And then now, how did this research evolve? I mean, I was chasing my colleagues from Schneider, Dart Logistics, different companies, just to see how things are going. At one point, actually, I visited Green Bay, Schneider headquarters, and I worked on this research, the NSF support research, also with Tom Ferris at X&M. That he's on the human factors. We got in touch with the drivers themselves. After I started this research, I actually started following trucker forums, just to get that perspective too. Because that's, like I said, the three stakeholders. That's the easiest way to really get a sense of where they are, where they stand, what are the issues that they're dealing with, and so on and so forth. It's not easy life. It's very, very hard, very, very hard, really. And so with that research, now there are a couple of very encouraging things. One is that, for example, with the electric vehicle and the refueling, alternative fuels, and all this, all of a sudden, use of relay networks is applicable in those alternative contexts. It has applications, obviously, in the communications context, where the signals has to be regenerated, right? But more importantly, it is for the whole industry. It's not just for like one company to operate in that fashion, but the whole industry. Now there's the load boards, all this IT and the apps and all that stuff available, right? I mean, matching the loads, there are a lot of older operators, smaller trucking companies, less than 30 million revenue, right? There's a huge amount of them, right? It provides them really the access point, right? Mm-hmm. Just go to the load boards, go to those relay points, see what loads are available, right? So it can make this operation and matching happening naturally, if there is such a system. And speaking of that, so it's a good thing for the whole industry. I also talk with a, we got connected because I follow transport topics and some other the outlets on LinkedIn to see what's going on in the industry. So I kind of chased from there. There was some talk on relay points. I said, like, who's talking about this? And then just sent some emails around, and and then I reached Jeff Svensson. He's a yeah, he's a person that I got equipped. I never met him in person. Actually, we just talk over the Zoom and all this. He's actually in the real estate business, and we talked a lot. And I talk about these things with him too. Um, he was starting with how do you set up those locations, service locations, not to get the trucks into the cities, around the cities, in the satellites, right? But now moved more into like how do we set up these relay networks, right? Or but as a real estate, I mean, literally, he's interested in building a network like this, which is very encouraging. I think. I mean, if it works out, um, with um, with the technology that we have now, it should not be too difficult to operationalize it. And I understand that there's some actually companies, startups out there who are already thinking about operationalizing uh, uh, this kind of trucking, truck dispatching, and so on and so forth. So there are a lot of encouraging things that are happening around relay networks, which which is very good. I mean, I feel happy about that, really. So so that's one area. Do you have any questions for me before I talk about something else? I think I covered pretty much everything, like from the starting point,
Yeah, I
kind
wanted
of
to
things
go in
that we
on.
did, how we do it, and then to where it is now and where it is going, even like out of my sometimes
Well,
reach.
I'm glad too that you closed the loop on the visual of you chasing executives around at conferences trying to
Yeah,
get some of this data. I'm glad you
yeah,
mentioned
yeah,
that you were able to find some of that and make some progress there. But I
yeah.
wanted to touch on something else that we talked a little bit about before we got on camera, and I think this is some good context to your approach to networks, systems, and the design of these. As you were talking about the relay problem, for example, you listed so many constraints, and I think this is what makes your approach and line of thinking so important too, is that you can understand so many different stakeholders and what's important to them. So could you talk a little bit too about maybe the difference or similarities between like networks and systems and the use of those terms, and then your approach to problems like this as well?
Sure. I mean, networks are sort of like from our perspective, integral part of systems. We represent the systems that we work on as networks. So sometimes we call it network systems. So the entities, the resources, where they are, how much they are available, and what do we require from that system. What's our objective? That's all happening in the medium that is represented as a network, right?
Mm.
So almost in all my research utilizes some underlying network. So we're always in need of some data. So if we can find it, we use it. We find it in the contexts, for example, in emergency preparedness and the biomass from the government sites, and we use GIS quite a bit and the geographical information systems. So we import whatever data that we can find there, and if there are any gaps, we fill in a way that makes sense. Really, I mean, that's you have to be very careful there because um, the way that you generate the data or fill in those gaps can actually have ultimate effect on how your algorithms are running. So um, it has to be sensible, and sensibility is an issue. Of course, there is a defined, but what we do is that we look at the scalability and the scale, in other words, of the data, right, with respect to each other, and that what we have available and what we are producing, and also in the end result, when you look at those costs, you cannot have your, I don't know, like fixed costs in the millions and your transportation costs in the tens or hundreds, right? So that's not how it is in the real life. So we try to achieve a balance there, and also make the data, drawing from the real life data as much as possible. And usually problems, some challenging problems come in when things are like that, really. But eventually, the network that you have, whether it's cost data, capacity data, um, uh, it has the demand data, right? It's all on the network, and that's what's representing your system. And when you're optimizing, you're writing what we call the system model, really, right? And in that system model, of course, you have those different perspectives now. Now, how do you take all these into account, right? I mean, um, you have one model, but three stakeholders represented in there, right? So you're just looking at their objectives, the things that I listed for example, for the driver, for the customer, and for the company, right? And then you write your constraints and your objective function in a way that you can tell, okay, this is really serving my customer point of view. This is serving the company point of view, and some things are serving both, right? But overall, the model is capturing all the stakeholders' point of view. So that's the important thing. If I look at it, uh, um, for example, only from the company's point of view, I would probably not even set up a relay network. I can never make it work because they will never want any security.
Yeah.
So so this is how we think about it.
So then I think too from there you could kind of lead into one of these other projects that you mentioned earlier. Maybe if you want to go into the biomass project or one of the other ones too. Kind of give us a
Yeah,
rundown of what that project looked like as well.
sure. In the biomass one, um, we like I said before, I think that was before recording maybe. I started that research um, in collaboration with my colleagues at the University of South Carolina, I think they were at the time, and they approached me with the problem that they're working on the biomass supply networks, and they wanted to collaborate. So we started the talks then, and then they visited me at Texas A&M when I was there in the INC department, and we worked on that. But then after that, I started thinking about that a little more and then extending it. And then what we did there is that instead of just assuming that, okay, these are your supply points, you're getting your biomass, so it has to move through your collection facilities all the way to biorefineries. Ethanol is produced, and from there, ethanol is sent to blending facilities, which are the oil refineries where the ethanol is blended with the regular oil, and then sent to the pump, right, to gas stations. So that's the typical supply chain there. And there we said, okay, we actually are dealing with an agricultural product, biomass being, and the supply is actually coming from farms. So the farmers themselves are stakeholders here, right? So if they don't plant, we are looking at switchgrass and corn, that kind of stuff, not like the forest residues where there's some planting involved. So somebody has to make the decision. So when you look at it that way, well, they are definitely stakeholders because if they don't plant, we don't have supply, right? So we want to ensure a certain amount of supply so that we can get this 10, 15% ethanol in our gasoline, right? So, but how do we ensure it? So we cannot just um, assume that we're going to get that much, or assume that people will plant, the farmers will plant those, and then we're going to get what we need, right? So, so we said, and that's interesting because um, the idea came from here. I'll tell you where the idea came from. The first one. When I was a kid, we didn't have TV, we had radio. And on the radio and the news, there was always this announcement that government announced the price for this, produce, for that produce kind of thing, right? It's like a base price, maybe. I don't know. I was a kid. I really didn't know. But what I remember is that there was some price announced for the farmers.
Mm-hmm.
And then I said, okay, why don't we just promise to purchase price, announce some promise to purchase price or offer promise to purchase price to farmers so that we are competing with tomatoes and potatoes, right? So we beat them. We beat those other crops. And the farmer plants the switchgrass.
Mm-hmm.
Now, so then the decision is what the price should be. And it may change depending on where the farm is, right? That's another thing. Because some farms, we might be more interested in getting their stuff because it is logistically more attractive, right? So there is a logistical component to it. It's not just the price and the supply is available that much here, but I'm going to collect it. So I'm going to set up a network. So that's going to cost me money too, and it's a large part of this logistical operation. So then how do I combine the pricing decision by bringing the farmers as the stakeholders, right? With my logistical decisions, collection network decisions on a season basis or the yearly basis, right? Because those can change. And then how much profit, of course, the bio refineries will make, or that will be coming from the blending side. So bringing all these together is where the stakeholders really are coming together in this case, right? So you cannot just offer good prices for farms here, but set up your collection centers here. So it has to be make those decisions in an integrated fashion. So so that was the main motivation of it. So we started from there, and we worked on this pricing and the logistics network design decisions in an integrated fashion, by also, of course, taking into account the yield variability, right? Because it is not that a farm is going to plant it or not a farmer, but it's also how much yield that will be coming from there. It depends on the weather, it depends on pests and all that stuff. There's a lot of things that affects the yield, right? So taking that as a component of uncertainty into the models, and the initial work was supported by USDA on that one, and for the extension, we'll probably I'm actually extending it now, working with another graduate student to agricultural networks. So this is where it is going now from our perspective, because we realized in the last few years that the agricultural supply networks, they also have some problems, and then we know some things from the biomass side now, and then the pricing mechanisms can be actually, we just became much more aware of the literature, of course, once we got into that, and there are different pricing mechanisms that you can announce prices, but it's not like still the farmer makes a decision, or it can be, you announce a minimum price, the farmer gets the price in the market, right? But if it is below the announced price, government or the supplier gives the extra to get whatever product is available, maybe. So there are like different mechanisms involved in there. So how do we get those into the equation, but still integrating with the logistical network establishment sort of costs and decisions, right? Because they always go together. Eventually, that is the bulk, other than the production of the crop, that is the bulk of the cost involved in there. In many places, probably in the US too, but I know in other parts of the world, those costs can be so prohibitive for the farmers, the transportation costs, right?
Mm-hmm.
If those networks are not designed carefully. The farmers literally leave the produce in the field instead of harvesting it, because they lose money if they harvest. Harvesting costs money, transportation costs money. So they just leave it on the, and that of course inflates the prices in the market because there's not enough supply coming.
And then two, I think we'll run through your emergency preparedness research if you want to give a brief overview of that, and then
Sure.
I think after that I have some follow-up questions. I'll dig into some of this.
Sure. So in that one, that emergency preparedness, that started right after Katrina, but not in a way because of Katrina. It's definitely an important thing, of course, that we experienced, and it was a very significant experience for a lot of people, and actually that what it led to shortly afterwards, when Rita was projected to the landfall in Texas, right? Houston, Galveston area, that area. The evacuation was enormous because almost 2 to 3 million people evacuated, and they didn't know where to go. Shelters were full. There were not enough shelters, and I was in College Station at the time, obviously. So there were a lot of people, just sleeping in gas stations, side of the roads, and the shelves are empty and all this. So then we said, okay, like we bring all that stuff from all the way from China, right, so to speak, at the time, and it's still for pennies and make profit out of it. I mean, like by that I mean like logistically we can be very, very efficient, right, to move things around. So how come we cannot do this? I mean, why these people do not have to go through this, right? So and it puts a lot of stress on in other cities too. It kind of cascades in a way, right? So so this is how we started that, and when we looked at the literature, we have seen evacuation studies which seem to be like very, very relevant, right? So we looked at that first, but then we realized that given that there's a relief supply issue too, there were some studies on that too. Then it occurred to us that, well, you cannot really think of these two parts in isolation. Again, they're part of the same system. And you have your stakeholders being the evacuees in the first place, and the officials are making decisions on evacuations, and the officials are making decisions on the relief supply, right? And those two officials, they're just doing the best that they can for their part, but they're actually contributing to the same operation, right? So it has to match what their decisions are, and where it has to match is where the shelters are. So that's the interface, and the whole thing is the system. So we said, okay, we just have to look at this as a system with these stakeholders, right? So and then we started, okay, where do we set up those shelters? How do we make those decisions, right? Setting up the shelters and where people go, how do they get there, when do they leave on the evacuation side. On the supply side, what amount of supply of each different supply source, can be medical supplies, food, and etc., and where, how much, and how to mobilize them, when to mobilize them. So when you have this whole operation started, evacuees, when they go to their guided location, go there, they find the supplies that they need there, right? So that builds trust in the system as well, right? So there are a lot of benefits of doing that, not just the logistical benefits, but also it helps with the compliance too, right? Once people know that this is how it is run, right? And they will not be just going to one location and somebody will say, oh, it's full, go try this other one. And they go there, they find a location, but there's no water because nobody, complained that there's no water. Now they complain and the water is coming the next day and all that. So we're trying to avoid all these complications in a way. So how do we set up systems that kind of addresses all these things in an integrated fashion? So this is how we started that. That also was supported at one point by National Science Foundation, and and we still continue working on that research. There is still things to do, really. And one thing that we are doing right now, in addition to all the network design related studies, we just started this semester our research on understanding people's decision making. How do they make decisions, and what data is available out there? Because there's a lot of social science studies on that front. We're trying to get a good understanding of that, but not only that, because when you look at those studies, most of the time what you see is that, okay, after this event, this is how people reacted. After this event, this is how people reacted. They're specific to certain events, right? But the question is, how do we draw overall behavioral patterns, decision-making sort of patterns, right, in those situations? So hopefully we just finished preparing some surveys on that of the public, and use some prediction tools, data science tools, really, to extract that information from existing studies as well. So those are the things that we are looking at, just to incorporate those into our models actually later. So there's a lot to do still on that front, especially given all the the crazy events happening all the time, not just in the US, all over the world actually. Yeah, that's another thing that we do. I mean, we are motivated by the events that we see, right? This is what kind of like triggers it, because they're much more immediate that we are aware of them. But then once you think about it, all over the world, these things are experienced by people. It's not just here, everywhere, right? So we try to bring in that perspective at one point when we're working on these problems. Yeah.
Yeah, I think behavioral science is a term I hear a lot too that kind of touches on what you're describing too. But I know we could go into that. You have a lot more great research, but I want to kind of condense some of the lessons and learnings. I know just from like those three examples you ran through, I already saw some recurring themes. So I think you have an interesting vantage point to get to see networks on so many different levels, right? To look at it from like this biomass kind of agricultural lens. You've worked with trucking companies and transportation logistics, this emergency preparedness. They're all so related. So what are some of like the recurring themes you see whenever you go and look at a network? Like what are some of the problems or opportunities, or your thoughts as you work on some of this research, and where do you think the future of kind of network design may be heading?
Yeah, definitely. So one thing is that really representing the realities of the operations and the people's decision making from coming from those different stakeholders, right? How do you incorporate all that into the design of your network, and how much of a granularity that you look into when you're looking at your networks, right? And that can be not just the nodes and the arcs perspective, but also the time. Because sometimes we work on, like in the evacuation networks now, we work on time phase networks, how things are evolving in time in the network, right? So we did a study a long time ago on natural gas distribution networks. That was the first time that we kind of worked on that. That idea came up. Like, what kind of a granularity that you look at time-based wise? Do you look at your network evolving or the things flowing every, say, 6 hours, or every 12 hours, or every day, right? So that affects how much data that you have to be dealing with, right? So, and how long of a time horizon that you can look into those decisions. From the modeling perspective, incorporating those operational needs and demands at the strategic level in the correct way, so that they're representative, really, right? that's a challenge. That's like a very high level conceptual challenge, right? Like I say, we do the distance constraints between those relay points, right? So that's a good way to keep the drivers close to each other, close to their domiciles, right? Their home bases. Or say the circuitry constraints. So that keeps them the loads not to take too long, right, to reach. But that's a proxy. Like how successful is that? I don't know right now. Like, is there another way? Because I know that operationally I need those things, right? But I may be setting a constraint there where my operation is here, right? Or I may be setting a constraint here where everything is operating here, pushing the boundary, right? If I release this a little bit, maybe I'm going to be having more room and my cost maybe will just go down significantly, right? So we do that computationally, those kind of studies. But is this the way, or is there any other way to take that into account? So 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 answering that would be, I think, would be very valuable because at the end you are operating on these networks, right? That's probably a challenge. Maybe it's been a challenge always, right? We make strategic decisions, but then we face what we call unintended consequences. Well, that's because we didn't know how it will translate into operation, right? So this is exactly what we call unintended consequence, actually, if you think about it, right? So how do you do that so that you don't cause these unintended consequences, right? So I think that's a challenge. Getting data, representative data, is of course the challenge, right? Because you can always, I mean, we see that but that's one reason we do so many computational studies. I mean, sometimes my students say, okay, didn't we run this enough? Like, it's always in the beginning, we always look at are there any pathological cases here, right? We try to understand that. And then we try to verify the model and validate it and all that stuff. So because you don't want to be running on some garbage data that really doesn't represent the real case, right? So developing those data sets and also keeping them available, right? And refining them, improving them. Like we publish our data, whatever that data that we used in our studies, it's on all on my webpage. They're always there, so for anybody to use. And anybody has any, the improvements over it, of course, we would like to hear, like the additions to it and all this. So but it would be really good if there was like a greater repository for some fundamental problems. There's really good repositories. Beasley, for example, or our library. We still go back to it many times. It's been around for a very long time. Very, very useful. But for these networks, for specific applications, there are enough people working on them, right? But I think it would be really good to have repositories on these. And like I said, from the modeling perspective, once you know what you're going to model, it is not that big of a deal. I mean, we do this is what our trade is, right? Yeah. So we do that. More important is what is it that you're modeling? How do you decide what to include, what not to include, and if there are alternative ways to model, which one is better, especially from the development of the solution algorithm perspective, right? So we use, like, for example, I use a lot of Bander's decomposition. I started doing that in the beginning. We did some work on closed loop supply chains. We started with that on the sustainability front. We had an NSF grant on that, and we started working on this with a graduate student of mine at Texas A&M. It was a collaborative work with Florida and A&M. And there we start with the Bander's work, and then I actually used it so many times after that because I find it as a very versatile tool. Because you can play with the upper bounds and the lower bounds. And that's what optimization is. From my perspective, really, I'm not looking for the optimum, but I'm trying to get the bounds as close as possible, right? So this is what we work on. So if the tool gives me opportunity to work on those bounds separately, right? So I can improve them, trying to get them closer, right? So instead of trying to pinpoint where the optimum is. So I'm a big fan of Bender's decomposition, and then we have certain ways of enhancing the approach. Plain vanilla usually doesn't work, but what comes out is a team again and again in those studies. You really have to understand the specific application domain and what you're modeling well, and those interactions, the system as a system, you really have to understand it well, so that you can generate certain constraints that will be sort of implied by, or they help to design those systems, motivated just by the nature of them, right? And incorporate these into your solution algorithms to make your algorithms much more efficient. At the end of the day, we need efficient algorithms because we end up running them for a lot of analysis, what if analysis and whatnot. So a lot, right? We want those things go. We don't have 3 days to wait. I mean, for 2% optimality gap, we want to get these quicker, right? And even a little lower, that's even better. That's whole another discussion, like what is the meaning of 2% optimality gap? You know, what the problem is, what the real problem is, and so on and so forth. I'm not going to go in there, but whatever that you're modeling, starting with that, right? Assuming that this is what you're interested in, the output, the outcome of that model is of use to you or to somebody, right? You want to get those results quickly because we use that a lot of for a lot of analysis. So understanding really the essence of it, not like blindly, applying this optimization algorithm to this problem, right? So in a way, like engineering the solution, right? That kind of a mindset should always be there, I think, because yes, we are applied mathematics. We have all kinds of people in our community, but it is engineering at the end of the day, right? So you have to engineer your algorithm, right, for the problem at hand. And you find sometimes common threads, what you engineer, that applies to other settings, which is useful. So we always, of course, keep an eye on that. What I did here, does it apply in that setting? That was the main motivation, actually, when we went into stochastic programming after so much Benders. We said, okay, we learned so much about Benders here, and the stochastic programming, one tool is the L-shaped method, which is essentially Benders. So why don't we just translate what we know here into the stochastic programming context and see how useful that can be, right? And some of these things were really not used in the stochastic programming, or I mean, that interaction was not explored much. Now it's actually really, really good. I think the stochastic programming community is marvelous. They're doing great things, actually. And but for me, that was the motivation. Going from the deterministic optimization to stochastic optimization, it was purely motivated by the tools that I use for optimization. I said, I know how to do these things, and I can make use of these things and maybe expand them in this domain, right? So for me, that was the motivation, really. But that can be generalized, for others to utilize as well, I think.
Well, you spoke a little bit there about the tools you use, and I want to ask you one more question about how technology is impacting your research and how you're kind of preparing for the future, right? With the explosion of AI in the form that is kind of taking headlines and quantum computing too. How are those impacting your work, and what are you kind of thinking for the future ahead with those tools?
Yeah, that's a great question. Now, it's mind-boggling how the things are evolving. So from the AI, the predictions or predictive analytics side, right now we are much more interested in that emergency evacuation and compliance for that purpose, what is the existing data, how we can make use of that. So that's definitely a point of application that we are working on right now. But in almost all of these, for example, take the relay networks, right? If you think of it in the context of the whole truckload industry, the load ports are there. I mean, you can have apps that will just daily recommend drivers loads to go pick up, knowing their location, where the load is, where it is expected to show up.
Yep.
It can say, okay, you're here, there's a load moving here, it's expected to be here at that time, and you can go meet that load at that time, at that location, and pick it up and take it to that place. You can enter what you want. I want to be at home at these times, right? Other than that, I'm flexible. I mean, it can do this matching. It's unbelievable. It can predict where the loads are going to be, how they're going to move, where the drivers are, and then it can make those recommendations to the drivers. Just make that system just flow.
Yeah.
I mean, it is unbelievable. And in the biomass setting, the farmers' decision making, we can look at past data. We can look at their decision patterns, how they make decisions. We can make predictions on what products, crops are more appropriate to plant next season, for example, in different places. So we can predict the efficiency of the soil at different times, right? Because there's always that cycling going on, right? You cannot plant the same thing in the same soil all the time. And so there's so much that you can do. I didn't go into quantum, but years ago, when I had a grant from NSF on sensor networks for environmental monitoring, there we were looking at the sensors deployed, wireless sensors with limited, battery life. So how do you maximize the lifetime of the network? So that, it can be like fire, for example, monitoring in the forest. It can be monitoring glaciers, monitoring different things like in hard to reach places where you drop the sensors and you collect data continuously, right? So that's another thing actually. Whenever you have a lot of data, the prediction AI kind of things come into the picture. And I'm not even talking about the LLM models and all this. I mean, you can make all this like a conversational maybe even. Right, with the truckload case. Well, anyways, coming back to here, to the sensor one, in the context of the NSF grant, we actually went to San Diego Supercomputer Center 2 summers. My graduate student spent her summers there, and we worked on some parallelization of our algorithms. They gave us about 10 nodes. We created parallel codes and all that, and I couldn't back into it after that. We were very much into it at the time, but now recently, with this evacuation and the emergency preparedness study, we have excellent resources on campus here at SMU, state-of-the-art high-performance computing facilities. Just for us. It is not like for state that you have to go by time and all this. I mean, it's available to us on campus. And we just started using those resources for the large-scale evacuation cases, the decision-making where you remember that I mentioned the time phase networks? Yep. All of a sudden your networks blow up, right? So you need more computational power because your number of decision variables increase quite a bit and so on and so forth. So we are getting back into that now, using the high performance computing that we have available on campus, and there's great resources here available to us, so we're using those. Yeah, but I didn't go into quantum, etc. But I mean, if you think about it, what Amazon is providing online, and it's definitely going to make it possible to handle larger networks with more realistic the models, and not only that, coming back to that, how one of the challenges, operational strategic decisions interface, simulation is a great tool there, because what simulation provides is obviously you insight into the operational issues, right, on the systems that you design. So with such high performance computing facilities, you can actually make that integration, right, to understand these systems better. And what do you know, that might actually turn into what people call about digital twins of networks, right? Because you have to have these digital twin. Yes, it's not simulation, but simulation, I see it as an integral part of it, because you will be doing a lot of analysis, right, constantly by collecting data and getting data back and forth between the digital twin and the actual system, right? So if you want to use those digital twins for decision making as decision making tools, you will have to have these optimization simulation methods embedded into it, right? So that as you're collecting, you're making predictions based on these decisions and their impact on the operational side too, right? So for those, I think those enhanced computational power will definitely be useful. It will. We will need them. It is not like a luxury. We will need to use those things. Yeah.
Well, especially as data becomes more readily available, right? I mean, I know for an academic use case, it's very difficult to find, but a lot of these companies are just pouring out data with the proliferation of IoT, smart sensors, the ELD mandates. I mean, there's a million reasons that they're getting all these data points. So being able to collect that and interpret it will be very helpful. But Professor, I want to thank you for your time. I know we've already gone over an hour here, and I think it's lunchtime here in Dallas, right?
That's right.
I want to thank you again for taking the time to chat with us. And for anyone who wants to reach out, what would be the best way to reach you?
Oh, email. My last name, Uster at SMU.edu.
There we go. Yeah. Well, perfect. Well, Professor, thank you very much, and I appreciate the time, and look forward to having you back on in the future, as I know we could continue to go on for a couple hours here. So
yeah, I know. We are academics. We like to talk.
Well, have a good day, and
thank you so much, Jacob. Listening. Thank you so much, Jacob. I appreciate it. Right.